There's something deeply enduring about shaping metal by hand. In a small workshop in East Stroudsburg, Pennsylvania, this timeless tradition thrives through the art of handcrafted copper spinning, a process that transforms raw copper into elegant outdoor post lamps. Here, machines do not replace the artisan. Instead, they extend his skill. The centerpiece of this work is not just the copper, but the craftsman behind the lathe, a vintage Grayboe model, breathing new life into a century-old technique. The journey of each lamp begins not with the copper itself, but with the form. A mold, turned from dense, smoothly contoured maple wood, is crafted to serve as the guide. This wooden form must be durable enough to withstand intense, repeated pressure, yet precisely shaped to ensure the final piece retains graceful, flowing curves. Once the copper disc is centered on the lathe and the form is secured, the magic begins. As the lathe spins, the disc blurs into a glowing ring of motion. The spinner, braced and focused, leans in with a long-handled tool, his control absolute. Unlike many metal shaping processes, this one is done cold. There's no torch used to soften the copper. Instead, the transformation is powered purely by pressure, skill, and muscle memory. Each pass of the tool coaxes the copper closer to its final shape, guided by feel as much as by sight. Midway through the process, a separate copper blank is briefly exposed to flame. Not the spinning piece, but a backup used to prepare for the next steps. This quick torching burns off any oils or residues that might interfere with shaping, while enhancing the grip between the tool and the copper surface. It's a small but essential detail that ensures precision in the final form. Back at the lathe, the spinner continues his work. The floor hums with vibration, and the warm glow of the spinning metal casts fleeting shadows across the room. It's meditative, watching movement become form, strength become subtlety. The copper begins to stiffen with each pass, its resistance rising. The spinner must respond, adjusting angles, adapting pressure, and subtly shifting stance. This constant dialogue between artisan and material is what separates true craftsmanship from simple production. The aim is not just to shape a piece of metal, but to do so with consistency. Repeatable yet never mechanical. Each shell must be uniform in quality, yet each also bears its own unique signature. No two pieces are exactly alike. Slight variations in color and contour give the lamp's personality, depth, and soul born from human touch. When the shaping is complete, the copper shell is removed from the lathe. Edges are hand-finished, surfaces cleaned, and final details inspected not by sensors or machines, but by trained eyes and experienced hands. There is no automation in this workshop, only trust in tradition and skill. These copper shells are not mass-produced objects. They are physical stories of patience, discipline, and artistry. Each bears the imprint of the spinner's decisions, corrections, and accumulated knowledge. In a world increasingly focused on speed and uniformity, this process stands as a quiet but powerful reminder. Craftsmanship still matters. Automated system organizes, tracks, and stores raw materials efficiently. Raw materials are automatically labeled with precise data and deposited into designated storage locations, ensuring accurate tracking, inventory management, and production traceability. System retrieves specified materials swiftly for seamless production flow. The system automatically transfers raw or semi-finished materials between workstations using robotic arms and conveyors, ensuring smooth, continuous flow. Advanced clamping mechanisms secure each piece precisely, preventing slippage or damage during movement. Sophisticated positioning sensors and control software align materials with high accuracy, enabling consistent machining and processing quality while reducing manual intervention, cycle times, and potential human error. Automatic chamfering in the ring forging production line is a precision process that prepares the edges of billets or forged rings for subsequent forming or rolling operations. Utilizing high-speed CNC-controlled chamfering machines, the system accurately cuts or grinds angled edges around the inner and outer diameters of the workpiece. Sensors measure each workpiece's dimensions and feed this data to the chamfering machine, allowing adaptive adjustments in cutting depth, angle, and speed. This automation ensures uniform chamfer dimensions across all parts, which is critical for achieving optimal material flow during forging and reducing stress concentrations that could lead to cracks or deformation. Furthermore, the automated system can handle varying sizes and shapes of rings without manual changeovers, improving flexibility and efficiency. Dust extraction and chip removal systems keep the workspace clean and protect the machine components. By eliminating manual chamfering, the automated process enhances production speed, consistency, and safety, while significantly reducing labor costs and the risk of human error in high-precision aerospace manufacturing environments. Closed-die billet forming precisely shapes heated billets using high-pressure dies, ensuring dimensional accuracy, material density, and superior mechanical properties. Multi-station billet forming involves sequential processing of heated billets across several forging stations, each performing a specific shaping or preforming operation. The billet progresses automatically through stages such as upsetting, preforming, and final shaping, ensuring gradual deformation and uniform material flow. This method minimizes internal stresses, improves grain structure, and enhances mechanical properties. The multi-station setup boosts productivity by handling multiple parts simultaneously, reducing cycle times, and enabling high-volume, consistent production of complex aerospace ring forgings with tight tolerances. Double-directional automatic rolling shapes rings by simultaneously expanding and reducing their diameters in two directions, ensuring precise wall thickness, roundness, and superior material properties while maximizing production efficiency. Sprays protective coatings uniformly to enhance surface quality and durability. The automatic heat treatment line precisely controls heating, soaking, and cooling cycles to tailor the metallurgical properties of forged rings. Computerized systems adjust temperatures, times, and quenching rates based on material specifications, ensuring consistent hardness, strength, and grain structure. Automated loading and unloading improve efficiency, while integrated monitoring guarantees quality and traceability, critical for demanding aerospace applications requiring high-performance, reliable components. The integrated hardness test automatically measures forged ring surface and core hardness using advanced probes and sensors. Results are instantly recorded and analyzed, ensuring compliance with strict aerospace standards while reducing manual inspection time and guaranteeing consistent product quality and traceability. Precision process creating complex metal parts from wax molds. Certified welding ensures strong, precise joints for critical parts. AS 9100 certification guarantees rigorous aerospace quality standards and consistent manufacturing excellence. Computer-controlled cutting creates precise, complex parts from solid materials. Quickly produces functional models to test designs before full production. Enables precise part tracking, identification, and permanent product marking. Ensures high-quality, non-destructive testing for critical aerospace components. controls all production steps in-house for quality and efficiency. Delivers parts significantly faster, reducing customer wait and downtime. Utilizes advanced equipment and software for precision manufacturing excellence. Meets strict tolerances for parts essential to safety and performance. Fast, accurate pricing provided quickly to accelerate project timelines. Engineered for demanding applications where failure is not an option. Produces parts in steel, aluminum, and other diverse metal alloys. Extensive machining capacity ensures flexibility, speed, and production scalability. Non-destructive imaging detects internal flaws for assured part quality. Handles large parts, enabling versatile machining for diverse project needs. Measures material strength and toughness to ensure reliable component performance. Delivers finished products by integrating all parts into final assemblies. Blanking cuts raw metal into precise billets for forging process. This raw material, typically steel or alloy, is selected based on the mechanical properties required for the final product. Heating softens the metal blank uniformly, making it malleable for forging while refining grain structure and reducing internal stresses. Forging is the process of shaping the heated metal blank into the desired ring form using high-pressure mechanical or hydraulic presses. The blank is first pierced to form a hollow shape, then compressed and expanded to achieve the basic ring dimensions. This process aligns the metal's grain flow along the shape of the ring, significantly enhancing its mechanical strength, fatigue resistance, and durability. Forging also helps eliminate porosity and internal defects, ensuring a dense, high-quality structure ideal for heavy-duty industrial applications. Roll forging is a process where the pre-forged ring is passed between rotating cylindrical rolls that gradually shape it to the desired dimensions. This method applies continuous, controlled pressure, refining the ring's diameter, thickness, and surface finish. It also improves the internal grain structure, increasing the ring's strength and fatigue resistance. Roll forging ensures uniform material distribution and dimensional accuracy, preparing the ring for subsequent heat treatment and machining operations. Heat treatment alters the ring's microstructure to improve hardness, strength, and toughness, ensuring optimal performance under high-stress conditions. Rough turning removes excess material to shape the forged ring. Hobbing cuts precise gear teeth into the forged ring surface. Quenching on internal teeth rapidly cools the heated area, increasing hardness and wear resistance while maintaining the ring's overall structural integrity. Quenching on external teeth involves rapidly cooling the heated gear teeth using a controlled medium like water or oil. This sudden cooling transforms the metal structure, significantly increasing hardness and wear resistance. The process is carefully localized to avoid affecting the entire ring, preserving its toughness, while strengthening the external teeth for high-load and high-friction applications, such as in gears or transmission systems. Dimensional inspection ensures the forged ring meets exact specifications using precision tools, like calipers, micrometers, and CMMs. It verifies tolerances, surface finish, and gear profiles for quality assurance. Hoi ChatGPT. Wax injection involves injecting molten wax into a precision metal die to form a detailed wax pattern, which replicates the final casting. The wax is allowed to cool and solidify before being removed for inspection, repair, and further processing. Wax mold deburring and repair involve carefully removing excess wax, seams, or flash from the wax pattern using tools or heated blades. Damaged areas are repaired by adding molten wax, ensuring a smooth, defect-free pattern for accurate and high-quality casting. Shell making involves repeatedly dipping the wax pattern into ceramic slurry, then sprinkling it with fine sand. Each layer is dried before the next is applied, building a strong, heat-resistant ceramic shell that will later hold molten metal during casting. Pouring is the stage where molten metal is introduced into the ceramic mold to form the final casting. Before pouring, the ceramic shell is preheated to remove moisture and minimize thermal shock. The selected metal, melted in a furnace, is poured into the mold either by gravity, vacuum, or centrifugal force, depending on the complexity and precision required. Proper temperature control is essential to ensure full cavity filling and avoid defects. After pouring, the mold is allowed to cool and solidify naturally or under controlled conditions. Once solidified, the ceramic shell is broken away, revealing the rough metal casting. Gate cutting involves removing the metal gates and sprues that were part of the casting's flow system. After solidification, the cast part is separated from these excess sections using cutting tools such as saws, torches, or abrasive wheels. This step prepares the casting for finishing and quality inspection. Grinding smooths surfaces and removes excess material from castings. Investment casting, also known as lost wax casting, is a precision manufacturing process used to create intricate and high-quality metal parts. It is especially valued for its ability to produce components with excellent surface finish, tight tolerances, and complex geometries, often requiring little or no additional machining. The process begins with the creation of a wax pattern, an exact replica of the final metal part. These patterns are made by injecting molten wax into aluminum dies. For high-volume production, multi-cavity tools are used to increase output and reduce costs. In cases where only a small number of parts are needed, such as in prototyping, patterns can be 3D printed using stereolithography, SLA, based on CAD models. Once the wax patterns are created, they are attached to a central wax sprue system to form what is known as a tree. This assembly allows multiple parts to be cast at once. The tree is then dipped into a ceramic slurry and coated with fine sand to build a ceramic shell around the wax. This is done in several layers, gradually increasing in coarseness and thickness until a strong, self-supporting mold is formed, typically between 3/8 to 1/2 inch thick. The primary layer, which forms the inner mold surface, must be carefully controlled to ensure it captures all fine details. After the ceramic shell is complete and fully dried, the wax inside is removed using a steam autoclave or flash fire furnace. This leaves behind a hollow ceramic mold that precisely mirrors the wax pattern. The mold is then preheated to around 1,700 degrees Fahrenheit to prepare it for casting and ensure it can withstand the thermal stress of molten metal. At this point, molten metal is poured into the mold. The metal fills the cavity, capturing both external features and internal details formed by any cores. Once cooled and solidified, the ceramic shell is broken away using mechanical or chemical cleaning methods. The individual castings are then cut from the sprue, and any excess material is removed through grinding. The final castings are cleaned and may undergo additional processes such as heat treatment, non-destructive testing, NDT, machining, or surface plating, depending on customer requirements. If traceability is needed, identification numbers are engraved directly onto each part. Investment casting is widely used in industries requiring high-performance components, such as aerospace, medical, defense, and industrial equipment.